Good morning, everybody. I'm Einat Lev, and I'm a volcanologist at Columbia University, and the PI on the Victor project. One of my research focus areas is lava flows and how we can model them and study them. So today's lecture is about lava flows, and with the focus on modeling as well as the tools that are available on Victor. I'm sure for this crowd, I don't need to explain how lava flows are super important and how they can cause lasting damage. But we can, just get a reminder. These, for example, are pictures from the 2018 eruption of Kilauea volcano in Hawaii. And in this satellite image, you see the before the eruption layout of a little town called Vacation Land, with all these lots, have houses close to the ocean, and agricultural fields. And then this is how it looked after the 2018 eruption. And now this whole area is closed. The roads are done. They haven't been renewed or anything. So this is how it looks now. This is Leilani Estate, another subdivision in Hawaii. This specifically here is a geothermal power plant, and this is how Leilani looked afterwards. Leilani has been a little bit on the mend. There's some new houses and reclaimed areas, and the big road that went through this part of the flow field has been repaved and rewalked. So it's starting to be recovering, but this whole thing really is just there to like this. This is again the power plant and how close the lava flows got to it in 2018. It was very, very stressful for everybody, especially that there was a lot of toxic chemicals that they had to evacuate. Here, another mitigation example is how they tried to insulate some of the wooden power line poles with Tephra blankets and some reflective materials. Many of them did get taken down. Another more recent big effusive eruption that made a lot of headlines is the one in Cubiervieja and La Palma in Spain, the Canary Islands, where many, many structures and many fields were devastated by this eruption. You can see in this video, just from a drone, how there's the fires that are caused by the lava. A lot of times, in Hawaii, I was just there and we talked with local residents, and they said, a lot of times the lava didn't get to the houses, but the fires did. You can see this type of flow where it's all covered in rubble and just progresses very slowly. It's called a'a. More famous eruptions recently in 2021, and ever since then, pretty much continuously on and off, are the Fagradalsfjall or the Reykjanes Peninsula flow eruptions in Iceland. This is from the very first one in 2021 that happened after close to 800 years of quiet. So a lot of the residents were surprised, and a lot of the facilities were not ready for it. But now, they're getting very much used to it now. This is some of the mitigation efforts that were done. They're trying to build dams to protect some of the kind of roads that are downslope from this eruption. This is how it was constructed in the very beginning. But then some of the dams were overtopped, and then the lava flow started going down towards the main roads. This is in June, and this is later that month. You see that lava flow really progressed. So there's a lot of devastation and a lot of damage that are caused by lava flows. But lava flow modeling and simulation have multiple goals. And short-term forecasting, there's an eruption, there's lava flow. Where would this lava go? How quickly would it get there? This is just one aspect of why we need to model lava flows. Another is for hazard assessment and planning, more long-term. Where will some of the lava erupt from? Where would they go? How hot, dense, or fast will they be? Which, for example, is an important input information for people planning important critical facilities, power plants, shelters, and things like that. There's also a lot of information that is inside old eruptions, products, and old lava flows. So we would like to understand what they mean. What was that eruption fusion rate? What was this lava like? This is important information that can feed into calculations of the, for example, thermal or chemical budgets of the crust, of the mantle. And then we want to understand lava flows because they make such a big impact on our landscape and the biological environment and the living environment. So we want to understand how landscape, rheology, pulsing, cooling, all these fundamental processes interface with each other and impact our environment. And for all of these, it's also important to understand how uncertain are some of these above assessments. So if I say a lava flow would go this way, how certain that is? What is uncertainty on that? Or the arrival time. It's important, for example, for transportation department or civil defense to know when will this lava flow get there? Do I have a day? Do I have a week before I have to evacuate this town or this subdivision? And how uncertain that is. Because if I evacuate someone tomorrow and the lava flow doesn't get there until next week, that's a problem because maybe they could have rescued a lot more of their belongings. There are different categories of lava flow models. One of the kind of traditional division is between physics-based versus rule-based, where in physics we solve the fundamental equations of conservation of mass, energy, and momentum, versus rule-based where things get affected basically simply on, is this cell next to me lower in elevation, for example, or is the lava old enough, cold enough to stick around, to not advance? Another way to characterize models is deterministic versus probabilistic. In deterministic models, we put some input parameters and answer the questions of where, when, and how by solving equations, or we always get the same answer because it's always following either the same rules or the same physics. A different type is probabilistic or stochastic models, where it also answers the where and when, but also but with a different approach by looking at what is the probability of the flow to go someplace. This could be by modifying the topography, modifying the direction where the lava would go, based on some probability. But this division is a little bit more abstract because any deterministic model can actually be run in a probabilistic framework if we have enough computing powers. We can just run a deterministic model, but run it many, many, many times if it's quick enough, so that and then vary the parameters within our probability space and get a likelihood space at the end, even though the forward model itself was not probabilistic. I hope this makes sense. There is also different categories. There's a whole range of lava flow models, and they vary in complexity of the physics that is being considered and the numerics. The simplest models are models that you give topography data in a digital elevation model, DEM, and the location of the vent, and just let it go. So these would be models like downflow or multiflow that just follow the steepest ascent path and say the lava is going to go from this vent downhill, and this is how it's going to be. Slightly more complicated are the cellular automata or the lobes-based models. Some of these names include MagFlow, Molasses, Mr. Lava Loba, and QLava, where the model is discretized either on a grid or by kind of lobes of lava, and they advance from cell to cell based on a rule. Going forward a little bit in the complexity, the depth average models, such as Flogo, VolcFlow, IMAX Lava, missing Lava 2D here, we'll talk about that. And these solve the physics equations or the conservation equations, but they make a lot of assumptions on, for example, the lack of vertical velocities or some sort of a known internal structure of temperature and viscosity to make the solution much faster than comparing to fully 3D models. These come usually from engineering types of computational fluid dynamics models that have been adapted to solve the equations for lava flow conditions. So these guys are often very, very insightful, but they take a long time to run, which is not something we can often afford, especially during a volcanic crisis. So this was an overview, and what I want to do now is go through examples of some of these different tools and kind of explain a little bit in more detail what each of them does, their strengths and weaknesses. Downflow, as I said, is one of the simplest Colwood models out there. The way it operates is you take a DEM, put a vent somewhere, and then go through a number of iterations that the user sets to modify the elevation at each DEM point by a random value that you set between an interval. This can be plus minus a meter, plus minus 10 meters, whatever the user set. And then trace the steepest descent path from that kind of updated DEM and look where it would go. So the colors that you see at the result indicate how many of those traces went through each DEM grid cell. So the kind of the reds are places that were visited by lava in many, many of the iterations. And the yellows only got visited in some of the variations. Then for the summary, it's the probability of inundation. See that it doesn't tell you when that lava flow is going to get there. In the most simple models, it doesn't even tell you where it would stop because it just goes all the way to the ocean or to the end of the DEM. There is some versions that allow you to calculate kind of stop the flow by a known distance or stop the flow when an additional calculation of the lava age or cooling has determined that its viscosity got too high. These are some examples where downflow was used. For example, at the 2014-15 eruption of Fogo volcano, that was very devastating for the community. There's 2 villages that got destroyed, as well as many agricultural land. There's a really impressive video of how they were rescuing a lot of the wine barrels from the wineries, because that's the main industry there. And this is just another eruption of Mamotombo volcano in Nicaragua that I simulated on Victor. And all I changed was the that amplitude of that random elevation change. So when I didn't change that elevation very much, the lava flow went through this main channel and then got kind of spread over, because this area in reality is pretty flat. So without major changes to the topography, things are not going to get very focused. If I made the elevation change bigger, like 5 meters, then flows stopped more because there were more kind of barriers created by that random variation, and even more for a 10-meter size randomness. So it kind of got through the channel and then kind of stopped. Downflow is very, very fast, which means it can be used fairly efficiently to develop hazard maps. What people do is have some distribution for the likelihood of opening a vent. So there's a density function for vent opening. For example, it's more likely to be in this area than in this, but you still want to run those. So then you put a probability for the vent location, and then probability for the downflow, and probability for the length, and then calculate over how many years, assuming distribution for all of these variables, where are likely the lavas are going to go. And this is an example for Etna. If we advance and we have downflow running on Victor, it's not part of the package right now because that code is just kind of a very simple implementation of that random steepest descent path. But if anyone's interested in using it, we can work with you guys. Cellular automata models have been established in volcanology for a long time. They're very popular. They are fast and pretty simple. The idea of them is that there's cells, usually corresponding to our DEM grid, and then there's rules for transferring lava between cells that have either a level of probability that is defined, some kind of randomness, noise. There's a rule based on slope or temperature. So for example, if I have lava in this central cell, based on the DEM, I may go to each of the 8 around it. And most of the time, the rule would be put the most lava towards the cell that it has the steepest slope from where the lava is currently located. Here is an animation that shows that, made by Chuck. So you see kind of the lava thickness as much accumulated over time on all of these grid cells over time. This is a diagram that shows how a code called Molasses, a cellular automata code that created by the USF team, Chuck and Laura. So you initialize the path, get the loaded DEM and all the input parameters, and then send in a pulse, distribute, and just do a loop like that. And then see, do I have any more lava remaining in that volume, total erupted volume that the user defined? And then once the code runs out of that volume, it spits out the output, and just saying what the flow would be and where would be inundated by the flow. These are some test cases of molasses for example, Tolbacic volcano. It's looking at the model sensitivity by calculating the real lava area where it intersected with the simulation area, and then divided by the real lava area. So it's the sensitivity parameter. There's also the Jacquard fitness parameter that is kind of a similar calculation, except it's lava intersection with the simulation. divided by the lava union, together, the lava and the real and the simulated area. Here's a run of molasses for the 2021 Fagradals field. This is the real flow field, and this is the simulated flow field. And you can see that it's very similarly filled out all the basins between the ridges. So I want to do an activity now where you guys would all go to Molas, go to the Victor platform and try to run molasses yourself. Here are some instructions that tell you how to get molasses installed for you guys by using the Victor setup. And then there's going to be a Jupyter notebook that will show you how to run it. How's people doing? People have results?
Is there a command to save the figure? Or
Yeah,
yeah,
I think if you do, if you stand on the figure and do a shift right click, it'll give you an option to open it in a new window.
got it.
And then you can
Thanks.
save the figure. So this input parameters that you're using that come default with the notebook right now, using a DEM for Mauna Loa volcano in Hawaii, and the location of fissure 3, which was the dominant fissure in the 2022 eruption. Another type of lava flow model that is also quite simple is QLava. It's kind of an different interface than some of the other codes we have on Victor. It's a QGIS plugin, and it uses a probability for dispersal that is similar to a cellular automata, that just based on the difference in height. So you see the largest probability is going to go to the one that has the biggest elevation difference between one cell to another. And then they have some sort of a reduced probability for dispersal based on the distance that the lava flow went away from the vent, which is the proxy for cooling. These are some test cases that we ran for lava flow that were run with QLava for Etna and for Nyiragongo. If you wanted to use QLava on Victor, you'd want to have the QLava plugin added to your profile. The way to do that is go to the Victor graphical desktop, open QGIS, and then under the plugin menu, you'll choose Manage Plugins and select Install from Zip file. We already have the zip file. It's in Shared Models QLava. So you guys can do that later and play with that model. My experience with QLava is that it doesn't usually simulate flows very accurately, but it's very, very fast, and it gives you sort of a distribution. It's a little similar to Downflow in a way. Another popular tool that have been used extensively during the eruptions in Iceland. This is a tool that is being used by the Icelandic Met Office to forecast eruption path. Is called Mr. Lava Loba. It's also sort of a rule-based model, but instead of distributing based on the kind of the square or rectangle grid cells, it uses lobes. So there's a parent lobe and then parameters that set the direction in which that lobe is gonna make a new one, or a child lobe. And there's a distribution for that area of opening and how big that lava flow would be. So this is based on a kind of a parameter that you get that's called the lobe exponent. That tells you which lobes are gonna sprout new ones. Is it only the youngest one or all the existing ones? So it's a range from 0 to 1. And then the direction that this new lobe is going to be relative to its parent. So this is how some of the simulations look like, and depending on the parameters of kind of that opening of the zone of where that new lobe would be compared to the steepest descent path. If it's very narrow, you're going to get very narrow flows. Or if it's a wide area, the lobes can kind of wiggle around, you get a wider flow. There's also the lobe exponent. Are all the lobes able to have to sprout new ones, or just the newest ones? Here are some test cases that were run. This is Kilauea 2014-15, and this is Etna. And the blue outlines are the actual flow. Here we tested it on Victor on the Fagradalsfjall 2021 DM, and you see that it is able to reproduce most of the main flow features. We have Mr. Lavaloba, so we're going to run it now yourself. In a similar way to how you just ran molasses, please go into Victor, do Victor setup, choose, I guess, a different number. You look what the number is. I think it's 11 for Mr. Lavaloba. And then once you have that folder, open a notebook and start running through the steps until you get a map. So again, we're going to give it 5 minutes and see what you guys get. And while it's running, you guys can look at the results that other students have had, because in previous classes, we asked them to put the results all together. So you can see the results that students put 2 months ago, 3 months ago, that compared their molasses and Mr. Lavaloba results. So you can see that the footprints that are predicted are very, very different, even though we have kind of the same DEM and the same vent location, but the parameters are quite different. For example, if you go to the Padlet board and click on the results by a student named Travis, who posted the results for different volumes set up for Mr. Lavaloba, you'll see that the lava flows get a lot further as you increase the volume between that kind of top right panel, bottom left, and bottom right. And only in the largest volume did those lava actually get to that low area between Kilauea and Mauna Loa and reached that main road that was the biggest concern during the eruption. Will the lava get to the road and when? So this is bringing us to kind of the next important question that people ask when they do simulation, which is how quickly will the lava get to places? For example, when do I need to close Saddle Road to traffic because the lava will get there and destroy it? And none of the codes we used so far, Downflow, QLava, Mr. Lavaloba, molasses, none of them can answer that question. So to do that, we need codes that and models that actually solve some of the physical equations. And to really know the speed that the lava is going to move, we also need to know how dense it is and its viscosity. If you look at the simplest equation for flow velocity for an Newtonian fluid in channel, the maximum velocity equals to the liquid's density, gravity, the square of the depth, and the sine of the slope, and 3 times the bulk viscosity. So it's important to know what the viscosity of your lava is. There are also equations for non-Newtonian liquids like the Bingham fluid, where the flow has to overcome a certain yield stress before there's any flow. And there's similar equations for a Herschel-Bulkley type of fluid. There's some models that exist that solve these equations. For example, PyFlogo is the code that solves those equations along a straight, kind of a channelized or 1D slope profile. VolcFlow, IMAX Lava, and Flow2D, Lava 2D are models that solve that, and you give them rheology, for example, and viscosity and density as input parameters. PyFlogo, based on the original Flogo model, takes slopes along a track. This may be your steepest descent path or any other type of flow path. Give it an initial channel width and thickness, flow temperature, crystallinity, and composition. From that, I would calculate the velocities, also means arrival times, width, thickness, crystallinity, viscosity, and temperature, and the maximum length that the lava would get. These are some published test cases where they compared field data for temperatures and velocities with the prediction of the model. You see that they sort of kind of match. We have PyFlogo on Victor for the sake of time. We will not demonstrate it, but you guys can install it and get an example input and data and try to run it yourselves. VolcFlow is a depth average approach that solves the equation of conservation on a DEM grid. And then usually it used to be a closed MATLAB executable, but after some efforts, now there's a version of it on Victor as well. IMAX Lava is a newer code that solves the equation of evolutions. So this would be the conservation of mass. This is the conservation of momentum. So you have mass times velocity, which is momentum, and all the acting forces, so gradient in pressure, the acting stresses. This is the gravitational pull, and any other types of forces. Then there is an equation that solves the conservation of energy. So that's the solution for temperature and the internal thermal energy, so density and heat capacity, and how it's been advected and radiated out and conducted to the environment. Here are some test cases. Again, we have already seen this one for the Fogo eruption. And this is the footprint and the lava flow over time. And these are snapshots of IMAX lava simulations taken over time. And you can see that as opposed to the downflow simulations and the Q lava simulations that we saw for that one, they just gave us footprint. Here we can see how the flow advances with time. So, for example, how long do I have to take all these wine barrels out of the winery? This is an example of running IMAX for the DEM of the East River Plain. This is the nuclear facility at the Idaho National Lab. And just looking at 1 day, 1 week, 2 weeks, how far are we getting from that really critical facility? At home, you guys can try to run IMAX Lava on Victor because it solves all these equations. It takes a little bit more time. it can take a few hours. So you just start the run and let it go until you get a map. Lava 2D is, I think, the newest code that takes this approach of depth average models. It makes some simpler assumptions compared to IMAX, which makes it slightly faster. But the idea is that it assumes that the flow is well mixed, so there's a constant temperature throughout the core, and then that there are thermal boundary layers at the top of the flow and at the bottom, so it is conducting a conduction profile into the ground. Then this temperature profile implies viscosity profile, so there's a core uniform flow core that has the same viscosity, and then temperature dependent viscosity through the top boundary layer. This implies a velocity profile and a velocity gradient profile. So this would be the chill layer that they assume is just the same viscosity. So the crust all moves at the same viscosity and create at the same velocity gradient, which translates to sort of a plug flow at the crust. So it has a uniform velocity and then a parabolic profile through that isoviscous core. So it's kind of a compromise rather than solving everything, and so including the mixing in the core, it's solving it. There's making the simplified assumptions, which helps it run a little bit faster. Lava 2D was benchmarked and tested compared to well-documented lava flow experiments that were done at the Syracuse Lava Lab. So this is a picture. This is a chute where the lava flows were coming from. These are thermal data with a forward-looking infrared camera, and these are the model results looking at advance over time. These are the flow thicknesses and the crust thicknesses across cross-section in the flow, and there's a kind of vertical cross-sections that show the flow thickness and crust thickness as it advances. This is a simulation of, I think, the 1984 eruption of Mauna Loa, which was a very bifurcated, very kind of spreading out into many channels flow. And you see that Lava 2D, for the most part, was able to reproduce some of these bifurcations into different lobes. So that's really cool. It also had an inundation time based on the flow velocity, telling them, how many hours it'll take to reach different points. Again, we have Lava 2D installed on Victor. I think the default simulation that it comes with is the Mauna Loa 22 topography. You guys are welcome to go ahead at home and try to run those. We will and then you can share the results on the Padlet. It'll be really interesting to see how it all works. I'm sure there'll be some bugs and questions. So by all means, use the forum to ask the questions during the week. Just to wrap up with the kind of the most complicated types of flow models are the computational fluid dynamics ones. There are different variations, like finite elements codes or finite volume codes, codes using particle hydrodynamics, like GPU-SPH. So these come from kind of the general computational fluid dynamics world and have been used for lava. For example, this is a simulation for a lava flow channel. We don't have most of them on Victor, but if there's a tool that you really fancy and want to try, we can talk about installing it. Lastly, there's different ways to assess models, such as benchmarking. We compare the performance of a model to a specific test case. We saw a lot of different test cases that are used, like Fogo, Mauna Loa, Kilauea. There's also a model intercomparison, so you just compare different models to each other. And we're developing a workflow and on Victor that would compare 4 different lava flow codes to each other. Just more about benchmarking. I'm gonna share the slides so that everybody can have all this information. There's also a very detailed series of papers that defined benchmarks for lava flows and then tested multiple models on those lava benchmarks. This is a full video of some of some of the benchmarks that is defined based on experiments at the Syracuse Lava Lab. This is a video of that experiment. We're be more than happy to keep the discussion going. If you have more questions, post them on the forum. And want to leave a couple of minutes now if people want to ask anything right now. Yes, Alyssa.
Hi. Mine didn't finish initially, but then I ran, I think it was line just under the model output towards the end, if like there's a variable called run_number. And when I
Yes.
changed that from 4 to 0, that did output the figure at the end. So I think it's just a simple, at least that one worked for me to produce the final figure.
Right, yeah, so we still have Aloba right now. We're gonna change that. Every time it runs, it updates its run number. So if you want to plot your latest, you want to look at the file tree, see what the highest number is, and change that run number to read that. What we're going to do is we're going to change the notebook very soon so that it will always look for that latest number and plot that one. So we figured that one recently that it was just really annoying for people to have to update that number themselves. But good job for figuring it out. So I see that Eduardo, it's finished but has an error. So yeah, okay. So it might be that kind of run number that it's able to plot the DM, but then it's looking to open that output file and it's not finding that run number. So you want to update it to a run number that actually exists. So if you look at the file number, the file names in the output folder, you'll see kind of the run name and then a 0001 or 0002. So you want to pick a number from that list, the highest number, and try to run that plotting again.